Hi guys, welcome back to the channel. In this video, I will be covering the electron configuration topic of the A-level chemistry curriculum. So let's begin. So electrons are arranged in principal energy levels, which is also called shells. And that's a picture of the electron shells. So they orbit the nucleus, and there can be numerous shells. So the bigger the principal energy level number, the bigger the shell number, for example 5, it would be more further apart than a number which is smaller. So for principal energy level 1 would be the closest to the nucleus, whereas 4 would be much further apart from the nucleus. And orbital is a region which can hold up to 2 electrons with opposite spins. That's a picture of orbital. And then next, the electrons are arranged into smaller subshells. And there are 4 types of subshells. The first one being S subshell, then P, then D, and then F. And the S subshell will have 1 orbital and therefore have 2 electrons, because 1 orbital can hold up to 2 electrons. And P would have 3 orbitals and therefore 6 electrons. And then D would have 5 orbitals, 10 electrons, and then F would have 7 orbitals and 14 electrons. So as you go on, there are 2 orbitals being added, and there are 4 electrons being added every time you move on to the next subshell. And S orbital have a spherical shape, so they're shaped like a sphere. And P orbital has a dumbbell shaped, as you can see on the screen. Alright, so you'd be able to see the principal levels and the shell numbers at the top. So we have 1, 2, 3, 4, and the sub levels below that, or the subshells below that. So you'd be able to see as we move on to the higher principal energy levels, so the higher shells, the number of subshells increases. So for example, in 1 principal level, we only have 1 S subshell. In 2, we add a 2P subshell. In 3, we would add a 3D subshell, and in 4, we would have a 4F as well. And therefore, the number of electrons goes from 2 to 32 from the first to the 4th principal level. And after that, so for example, for the 5th principal level, it would have the same number of electrons in its principal level, so it can't get higher than 32 because there's only 4 types of sublevels. Alright, so just remember that atom fills up the subshell in order of increasing energy. So the electrons would fill up in the 1s subshell first, then the 2s, then the 2p, then the 3s, then the 3p, and after the 3p, that would move on to 4s instead of 3d. And this is because the 3d subshell is higher in energy than the 4s subshell, so that's why it fills after the 4s subshell. Alright, so writing the electron configuration. So for example, if we've been asked to write the electron configuration of oxygen, which has 8 electrons, what we do is we take each subshell into consideration. And we know that the subshells they move forward in increasing energy levels. So we have to fill each subshell first before moving on to the next one. So for example, if we have 1s, we can't fill half of that and then move on to 2s. The whole subshell needs to be completed with electrons in order to move to the 2s one. And we know how many electrons each of these subshells can hold. So for example, S can only hold 2 electrons, and that's how we know when to move on to the next one. So for example, we have oxygen, which has 8 electrons. So we need to fill the first 1s subshell first. So that would fill up with 2 electrons. So how we write it down is we have the number of main energy level on the left, so this belongs to 1 energy level, the first energy level, so we would write 1, that would be on the left, and then write the type of subshell in the middle. So in this case, this is S, so we would write this in the middle, so it would be 1s, and then the number of electrons in that subshell on the right as a power. So we would have 1s2 for the first one, and we would repeat and we would keep filling the subshells until we have 8 electrons. So we have, let's say we have 1s2 now, so we have 6 remaining electrons. So we would move on to the 2s subshell, and we know the 2s subshell can only have 2 electrons as well, so we would say 2s2. So we have 4 electrons now, and we have 4 left. And then we have the 2p subshell, but the 2p subshell can hold up to 6 electrons, but we only have 4 left, so we would just write 2p4, and this would be the electron configuration of oxygen. And we can also represent the electron configuration by the spin diagrams. So for example, this is the spin diagram for oxygen. So an arrow represents a electron. So for example, we have 2 there, 2 there, 2 there, and 2 there. So we have 8 arrows, and therefore oxygen has 8 electrons. And a box is an orbital. So this is 1s orbital, this is 2s, and we know because and the 2p subshell has 3 orbitals, so that's why we have 3 boxes. And the arrow points in the opposite direction, so if we have 2 electrons in one orbital, the arrow will point in the opposite direction because of the repulsion, and as the electrons would be spinning in different directions. And all orbitals should be filled before adding 2 electrons in the same orbital. So in this case, for example, if we're looking at the 2p subshell, we can't have this and then both of the electrons in the same one, because this would leave the last subshell empty, and we don't want that. So that's why, to avoid repulsion, we have 1 electron in each of them instead of having 2 in one orbital. So that's how it works. Alright, so the subshell with the outermost electrons is basically the block of the element. So we have 4 blocks. We have the S block, the D block, the P block, and the F block. We can find the block each element belongs to by looking at the subshell which is at the end. For example, this has 3s2 at the end. Because it has S at the end, we know that it belongs to the S block. For example, copper has 3d10 at the end, we know that this belongs to the D block. And when ion is formed, the outermost electrons are lost. So for example, magnesium, we have 1s2, 2s2, 2p6, 3s2. So when we lose the 2 electrons, it's lost from the outermost electron, the outermost subshell. And aluminium, same with aluminium, we have 3p1, 3s2, 3p1 at the end. So when aluminium 3 plus forms, losing 3 electrons, we lose the 3 electrons from the end instead of from the start. But there are exceptions. So for example, chromium, it has 3d5 at the end, but when Cr+, when it loses 1 electron, instead of becoming 3d4, we lose the 4s1 electron. And it's the same with copper. Copper is an exception as well. So we have 3d10 at the end. So when Cu2+ forms, when 2 electrons are lost, it should be it should go down to 3d8. But what happens first is that the 4s1 is lost first, and then the 3d10 would go to 3d9 instead of the 3d10 going down to 3d8. And this is because in chromium and copper, 4s electrons are lost before 3d, and that's because to have a half full or full d subshell, because that gives them stability, and all elements want stability.